Bismillah, Assalamu alaikum warahmatullah. You're listening to the Philosophy of Science lesson on logic and mathematics. In the last episode, we explored how we use logic as a philosophical instrument for understanding sciences. So today, we're going to do the same for mathematics. What that means is we're not learning mathematical formulas or techniques as such. Rather, we try to look at how mathematics affects other sciences. So don't worry, yeah? I'm not going to give you math homework to calculate something. And I will explain things in a way that even if you're not good at math, you can still appreciate it. One way of thinking about science is by differentiating empirical sciences and formal sciences. Empirical science is easy to understand. Empirical sciences study natural objects. Natural objects are, for example, your body, your immune cells, things you can see in nature. On the other hand, formal sciences study abstract objects. Abstract objects are like symbols. So numbers are examples of abstract objects. You can't touch numbers, you can't smell numbers, because numbers are abstract objects that exist independently of the natural world. So formal sciences study that. Formal sciences also study formal systems. Think of formal systems as what govern abstract objects. So the logic that we learned last time, it is a formal system. And for you, linguistics students, grammatical theories are a formal system because they govern how words are syntactically structured, how words are arranged. So I tell you how I think about this. Imagine you've got a chessboard in front of you, yeah? Empirical science is when you study the chess pieces like bishops and knights as natural objects. You measure their physical sizes. You chemically analyze whether they are made of wood or glass. So that's empirical science. Formal science is when you study chess pieces as abstract objects, as a conceptual objects. You study their mathematical value, that bishops and knights are worth 3 pawns, and a rook, for example, is worth 5 pawns. And then you study their formal systems, like how do they move across the board. And you learn that knights can jump over other pieces, right? But bishops and rooks can't. So that's a formal science. And why do I teach you this difference? Because in life, just like in chess, if all you study is empirical sciences and you ignore formal sciences, you're going to lose. So being aware of formal sciences is a good first step to winning. If you understand the differences between empirical and formal sciences, it should be obvious to you that mathematics is a formal science. And numbers are just one of many things that we study in mathematics. In pure mathematics, for example, we can study numbers, different forms of numbers, rational numbers, prime numbers. Also, we can study quantitative changes, which are movements in numbers. For example, in calculus, we can also study the structure of those numbers. For example, in algebra, and we can study geometry to analyze abstract shapes and their properties. So all these are included in pure math. And from that pure mathematics, we can derive many applications. Examples that immediately come to my mind are probability, statistics, and blockchain technology. You most likely have studied probability and statistics since you were in school, so I'm sure you know what they are. But blockchain is relatively newer, so I'll explain that a bit. The simplest way I think about blockchain is that it's a collection of ledgers. Like when you run a business, right? You keep a ledger. You use a ledger to track financial transactions. So who buys stuff from you, when did they buy it, and how much did they pay for it. So a blockchain ledger is analogous to that. It contains data about digital transactions, and those data are stored in blocks of information. And those blocks have digital chains connecting them, which means if you change data in one block, it affects the next block in that chain. And it's created in such a way that you can't alter the data in each block. It's immutable. The way they do this is by securing it with cryptography, with a mathematical function called a hash function. An example of a hash function you might have heard of is SHA-256, which we use for securing the Bitcoin network. So basically, we apply mathematics to secure our digital gold. And all those mathematics are built up from what we call theorems. A theorem is a mathematical statement that we argue from axioms. I will talk about axioms in a minute, but a common example of a theorem is the Pythagorean theorem. It says that when you have a right-angled triangle, meaning one of its angles is 90 degrees, when you have a right-angled triangle, you have the hypotenuse, which is the opposite of that 90-degree corner, and you have the other two sides. So the theorem says that the area of the square of the hypotenuse will always equal to the sum of the squares of the other two sides. So c squared is always equal to a squared plus b squared. So that's the theorem. Another theorem that I find way more interesting is Gödel's incompleteness theorem, because this is the stuff that when I read it, I felt like, wow, really? I thought mathematics is perfectly founded rationally, but even mathematical reasoning is more problematic than I realized. It's technical, but here is the best oversimplification I can come up with. So Gödel's shows that if you have a complex formal system, like a mathematical system, which has its own axioms, its own foundational statements and rules, when you have a system like that, it can never be both complete and consistent at the same time. Now, I'll get you some links to the more technical explanations. I'll put them below. But for now, I think of the theorem like this. Imagine you're in a library, right? Like a Hogwarts library. So this library has all the books about itself, millions and millions of books about itself. The theorem shows that no matter how many books you have, there will always be a true statement that you cannot find in any books. In other words, the library can never be complete. So that's one part. Here's the second part. These books can speak because it's Hogwarts, right? For example, a book might say, the book on my left is correct. So statements in a mathematical system can refer to other statements. A book can refer to another book. That's fine. Here's where it's interesting. What if a book refers to itself? Imagine I'm a book and I say, no book in this library can confirm that I am correct. That creates a logical inconsistency, you see, a paradox. We talked about paradoxes in the last episode, so this is another example. It's a paradox because if there is a book that confirms I'm correct, then my statement is false. But if my statement is true, we can't prove it because it means we can't find a book within this library that confirms me. So that's how I think of the theorem. No matter how comprehensive our library is, it will always be incomplete. And there will always be books that are true, but we cannot prove their truth using the library itself. Right? If you don't fully get it yet, that's okay. Because the implication is simply this. The lesson that I take from the theorem is this. We respect our rational systems. We respect scientific systems, especially our mathematical systems. Now, no matter how much we respect a rational system, we must accept its imperfection. There are truths that cannot be proven rationally within the system. It doesn't mean we give up trying to understand the sciences, but we must approach it with humility. So don't think because you are a science student, you are perfectly rational and better than others. Okay? All right. All mathematical theorems, they are built from the ground up from axioms or postulates. In many mathematical contexts, they kind of mean the same thing. Mathematicians might not be happy I said that, but for our purpose here, they are similar enough. An axiom or a postulate is a statement that is accepted as true without proof. So they are the foundation of mathematical reasoning. A straightforward example of an axiom is this one. If you have 2 points, P and Q, there is exactly one straight line that can go through them. So that's one axiom. Another axiom is if you have 2 lines intersecting each other, they intersect at exactly 1 point. So those are mathematical examples of axioms. You don't ask why they are true. You just use them as starting points to develop theorems. I personally came across the word axiom initially outside of mathematics. So the meaning of the axiom is quite similar, even when non-mathematicians like philosophers or mutakallimun use them. Axiom means a premise that is accepted without a prerequisite argument. It is a statement that doesn't need to be argued for. This is important because if you remember in the last episode that in deduction, for example, a conclusion is accepted based on the premises. But why do you accept the premises? One of the reasons is that those premises are themselves the accepted conclusions of a previous argument. So you accept argument A because of the premises coming from argument B. You accept argument B because of the premises coming from argument C, and so on. And if you keep pushing that back, you're going to get to axioms, which are statements that you don't need to argue for. A simple example is this. When you and I are arguing about a scientific theory, we both unconsciously accept the axiom that both you and I exist, that we both exist as rational actors who argue about the scientific theory. Even if we don't agree with 100 different things in our lines of argument, we've got to accept that axiom to move forward. Another example is any proposition P and not P cannot be true at the same time in the same sense. For instance, if I put forward a proposition saying, I have a wife, I cannot at the same time in the same sense propose that I do not have a wife. So they both can't be true at the same time in the same sense of meaning. I'm going to get in trouble with philosophers, and more dangerously, I'm going to get in trouble with my wife. Axioms are so crucial in the philosophy of science. They help us think deeply about science and religion, for example, at least in the context of Islam. The reason is natural sciences are intensely empirical, and Islam is intensely rational, especially in its kalam and theological tradition. For example, I've read this translation of the book by an Islamic logician called Al-Ghazali. He taught me over 900 years ago that to be an Islamic scientist, you cannot dispense with rationality. An example that he gave is this. A scientist comes to you and he showed you that he can turn a rod into a serpent. So he can give you experimental evidence on how to scientifically turn a stick into a snake. And then he said to you, now you know I'm a great scientist. I just showed you. So you must trust me when I tell you that 3 is larger than 10. In other words, he asks you to give up a truth that you derived from an axiom, in this case, a successor function axiom. So he asks you to give up on that. Al-Ghazali teaches us that you've got to say, no, sir, that's not what experimental science is for. I still believe that 10 is larger than 3. I won't reject rational axioms to put my trust in you. I mean, I'm impressed. I would love to know the technology of how you rearrange the molecular structures of the rod and transform it into a serpent. But I won't give up my intellect because you have shown me something astonishing. Yeah, so that's one way how the understanding of axioms might inform your thinking about science and reality. If you think about it, mathematics is not a natural science itself, but it matters a lot to natural scientists and philosophers of science. So why is that? One answer to that question is mathematics captures patterns in nature. It is an expression in our mind of the pattern out there. Or more specifically, it expresses nature in the language of numbers. And that gives us quantitative strength, the ability to control elements of nature. Just think about the accuracies required to launch a rocket or to sequence a genome. We become that powerful partially because we have that numerical strength. And of course, since nature matters to science, the expressions of nature inevitably matter to the philosophy of science. For example, mathematics informs our philosophical decisions about science and the experience of nature. In microbiology, we use mathematical models to understand epidemiology, to understand how diseases like COVID-19 spread, for example. Those mathematical models influence how we philosophically value safety versus freedom. So you've got countries that did nationwide lockdowns, like the US and China. And you had other countries like Sweden and Japan who said no, the complete lockdown would hurt people's lives more. And both sides use mathematical evidence to go through those philosophical and political decisions. Another example is Bayesianism. Bayesianism is a philosophical position that develops around Bayes' theorem. So Bayesian philosophers of science say that we should use that theorem to update our scientific beliefs in light of evidence. So one simplified example is this. You feel knackered, right? You feel fatigued. And then you say to yourself, I might be ill. There is a 50% chance that I'm ill. So mathematically speaking, you assign a prior belief that you are ill at 0.5 probability. And then you take a thermometer and your temperature is normal, 37.2 or something. Now, based on that empirical observation, Bayesian philosophers would expect you to update your belief. Your posterior belief should be less than 0.5 now. It means you now believe that it's no longer 50% chance that you are ill. It will be like 5% or anything lower than 50%. So that's Bayesianism. The third one that I can think of is AI. As a lecturer, I've got to philosophically wrestle with the idea that it might be unethical to give students exams without allowing them to use AI, to use OpenAI's GPT or Google's Lambda or Meta's Sphere. Because the mathematical probability of my students graduating and then working without AI now is near zero. So why not our exams reflect that reality? And it's like medical doctors as well. I mean, I love and respect doctors. They have saved my son's life. But as someone who studied immunology and microbiology, I have a sense of how complex a medical diagnosis can be. So with all my respects to doctors, I'm not 100% sure that it is longer ethical for doctors to diagnose a patient without AI support. Because AI can calculate the probability, they can calculate the probable diagnosis better, and they have more access to data than human doctors can, no matter how much experience you have in your medical specialty. Maybe it's not a huge philosophical conversation now when I'm recording this lecture, but I doubt that will be the case for long. All right, I'll close with this. I think the best way for non-mathematicians to experience mathematical nature intuitively is through music. When you hear melodies, what you're hearing is a natural phenomenon, which is sound vibration. But it's not just random vibration, it's a pattern vibration across space and time. And that pattern in nature can be captured, can be expressed mathematically in our mind. For example, if you have a string of a certain length, its vibration produces a musical note. And then, if you mathematically measure the exact length of that string and then shorten it by half, so 50% of the original length, it will produce the same note, just one octave higher. What that represents philosophically is that you can use mathematics to predict natural phenomenon with precision. For example, this is middle C. So that's the musical note that we call middle C or C4. The frequency value is around 261 Hertz. Now, by using mathematics, if you shorten the string by 50% or you double the tension, you will double the frequency value and you get the same note C again, and it is one octave higher, which is C5. And you can do this with all the other notes, D, E, F, G, A, and B. And then if you play a melody, your whole being can recognize that pattern reality without thinking about it mathematically. For instance, you will sense that this is similar to this, just one octave higher. And if you arrange a bunch of them properly, you experience the beauty of that pattern reality. Alright, that's my lecture on logic and mathematics. Talk to you again in the future. Barakallahu li wa lakum. Wassalamu alaikum warahmatullah.